Alright guys, welcome back. Today we're going to talk about the last further circle theorem. This theorem tells you the relationship between a tangent and a chord. So that's why it's called angle between tangent and a chord. What we can refer to this is a shorter name as tangent chord theorem. How about that? So what this is about is that first of all we have a tangent crossing the circle with only one point right here at A. On the other hand, we have from A to B a chord. So this tangent line and this chord, they're folding an angle called BAS in this case. On the other hand, this chord is forming a minor arc over here from A all the way to B. And this arc actually was subtend a bunch of angles, but here's one as example. Angle C. Okay, to be precise, let's call that ACB. Okay, so ACB over here is an inscribed angle. And this theorem tells us that your inscribed angle that is subtended by the arc AB is actually exactly the same as the angle formed between the tangent and the chord. So this theorem is a little bit hard to understand, but one thing that we need to know is that this theorem will only work if you're only talking about inscribed angle. Okay, so only inscribed angle will be the same as the BAS in this case. So let's look at a visual demonstration. So here we have a circle with a tangent line. The tangent line is fixed. Right? The tangent line is passing through one edge of the circle over here. So we fix it over here. Right? Your chord is changeable, is movable. Right? So you can move your chord to different places over here, and so that means we'll be forming like different angles in the pink part over here. So let's say just to make it more general, let's make the angle like this big. Okay, the white point doesn't really mean anything, so let's hide that. It will only control the size of the circle, so it doesn't really matter for us. Okay, but what matters for us is that, for example, you are fixing your angle between chord and tangent like this certain degree over here. What this theorem is about is, if you think about a point on the circle, so that means on the edge of the circle, let's say in this case this pink point right here, right, this pink point flashing. If we drag that, if we measure an angle from one end of the chord to the other end, meaning something like this, okay, then you will realize that the angle that is formed between the tangent and the chord is actually exactly equal to this inscribed angle that formed from one end of the chord to the other end of the chord. Yeah, so that's basically it, right? And that will be true if you move your chord around. Okay, it doesn't matter where you are, this will be always true. Okay, one very special case will be if you move the chord passing through the circle. In this case, we are a very special chord. We actually call this chord a diameter. Okay, so you have a diameter. Remember the radius tangent theorem telling us that in this case, the angle that we're making between our chord, which in this case is diameter, and tangent, is actually 90 degrees. So that means if you actually draw an angle from one end of your chord to the other end, right, you are actually facing a 180 degree half circle over here. So that makes your angle over here 90 degree as well, right? And it is true that this angle has to be 90 degree because of the semicircle theorem, right? This semicircle theorem guarantees that this is 90 degree. On the other hand, the radius tangent theorem guarantees this angle over here originally has to be 90 degree as well. So it kind of confirms both theorems that we learned before. So this is kind of cool. So let's work on a few examples. The first one, we are going to find x. Knowing the fact that CB and TA are parallel lines actually. So let's mark that down. If you have a parallel line, you will realize that this angle and this angle are actually the same because of the property of alternate angles. So the first thing that we will claim is CAT equals to BCA equals to x. Right? Both of them are the same, so you'll call this x as well. Right? The reason behind that is because we have alternate angles. And second, we will make use of the theorem that we use today. Notice that this point to this point will form a chord over here. And this angle x, this CAT angle, is actually the angle that is being folded by the chord and the tangent. And remember, at the same time, what is facing this chord, i.e. what is facing this arc over here, this angle, right, this inscribed angle, will also be exactly the same as your CAT, which makes this x as well. Right? So here you will say angle CBA is actually equal to angle CAT as well, and that makes all of an x. But then here, the reason behind that is because we have the tangent chord theorem. So there you go, you will see a triangle, and you know that the sum of all these angles needs to be 180 degrees. So you will have x plus 50 equals to 180 degrees. So you will have 2x equals to 130 degrees, and your x is just 65 degrees. So that's it for this question. Alright, let's work on 3 more different types of questions. This is on your textbook. The first one, now first of all, I hope we are getting more used to it. Let's first of all look at one chord over here, and then let's look at one tangent line here. The angle that we're folding over here turns out to be exactly the same as the angle, the inscribed angle that is also facing this chord. That means also facing this arc over here. Right, so these two are the same. So you can first of all claim that BAC is equal to 40 degrees as well. Right, so this is 40. The reason behind that is because we have tangent chord. So, and that's pretty much it for this question, because you know that this is equal to x as well, because we have isosceles triangle. So you have x plus 40 equals to 180. Okay, solve for x, we got 2x equals to 140, and x is equal to 70. Okay, so that's part A. Part B, again, let's look for the chord right here, and the tangent line is right here. This angle is 70, so this is the angle being folded by the chord and the tangent. At the same time, if you look at this angle, this inscribed angle, that is facing this chord and this arc as well, should be also 70 as well. So here you will say BAC is equal to 70 degrees, the same reason. And in this case, we have a little bit different scenario. Here we actually have 70 being duplicated instead of the unknown. So this is also 70. So we got 70 plus x equals to 180. X is equal to 180 minus 140, which is 40. The last one. Let's first of all look at this circle and realize that here we actually have an isosceles triangle, because both OC and OB are radius, so they are equal length. That will help you figure out one of the angles, OCB or OBC. Let's say in this case we call OCB. Okay, OCB has to be equal to 180 minus 70 first, and then you distribute that into 2. You get 55 for each. So each one of them is 55. Okay, and the second thing that we should realize is that OCT is actually equal to 90. Right, so this angle has to be equal to 90. Why? Because we have a tangent line over here, and then we have a radius over here. Right, so according to the tangent radius, we know that it has to be 90 degrees. And once you know that's 90 degrees, you're done. You basically can solve for x very easily. We got x equals to, x is basically the difference between a 90 degree angle and a 55 degree angle. So x is equal to 90 minus 55, and we get our answer, x equals to 35. And that's it for this series of questions. And that's all for today as well. Just a reminder, we have an online quiz covering all the circle theorems, but the Wednesday after the Golden Week, we are going to have a summative quiz on Unit 6. So I'll see you guys in the next lesson. Peace.